So very good morning to all. It is our great pleasure to welcome you all to the Knowledge 4.0 webinar series, which is one of the unique and distinct initiative of Chennai Institute of Technology, under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known first-generation successful entrepreneur, industrialist, managing director of MK Group of Companies. Under Knowledge 4.0, we have been conducting webinars such as Technical Webinar Series, Research Webinar Series, Career Guidance Webinar Series, Innovative Talk Webinar Series, and Alumni Webinar Series. Along this series, we are also conducting national, international seminars, conferences, workshops, and faculty development programs. Today, we have Dr. Anantharaj Sengeni, who is one of the leading researcher in Japan, and it is our great pleasure to have him for this wonderful forum. I welcome you, sir.
Yeah, thank you, sir. Yeah.
Yes, sir. So I have seen his profile. He's an excellent researcher. So far, he is having around 2,500 citation and 22 H-index. It is our great pleasure to hear from him. And Chennai Institute of Technology was established in the year 2010 by our Honorable Chairman, Sri P. Sriram. And today, our institute is being within top 10 among all other private engineering colleges in Tamil Nadu.
Yeah.
It is our great pleasure to welcome you, all the participants, along with our today expert, Dr. Anantharaj Sengeni. And now I request Harini, a student of first year, to introduce our today expert. Please, Harini.
Hey guys, this is Harini S. Persing, first year Triple from the Chennai Institute of Technology. As we all know, today's webinar topic is development in the electrocatalytic water splitting, including hydrogen generation. And we have Mr. Anantharaj Sengeni, Department of Applied Chemistry, Waseda University, Tokyo, Japan. He is a material and a molecular electrochemist working on the electroactivation of small molecules of importance in energy and environmental science and technology. He obtained his bachelor and master's degree in chemistry from the historical Presidency College, Chennai during 2008 to 2013. Being qualified in the national and the state level competitive test for lectureship and junior research fellowship in chemistry, he joined Dr. Subrata Gundu in chemistry with his group of CSIR, CECRI, Karaikudi immediately and completed his doctoral dissertation by 2018. Just before his PhD defense, he was awarded the prestigious JSPS postdoctoral fellowship by the Japan Society for the Promotion of Science during his PhD times for his achievements in the electrocatalytic water splitting. He was honored with the prestigious ECS India section SK Rengarajan Graduate Student Award for the year 2017 by the Electrochemical Society, USA. As of now, he published 57 articles in the internationally reputed peer-reviewed journal with an average impact factor of 7.2. His highest impact factor publication is 33.25 in the journal Energy and the Environmental Science. His articles are highly recognized by the international research community. As on today, he has a total citation of 2,260 with a H index of 22. He is currently serving as a reviewer of various journals of American Chemistry Society, Royal Society of Chemistry, Nature Publishing Group, Wiley, Springer, IOP Publisher, and elsewhere. We are immensely glad to have you here, sir.
Yeah, thank you, Harini, and thank you, Professor Dinaran, for your such a wonderful and very elaborated introduction of me. And I also thank the CIT administration and my good friend Dr. S. Raghavan for giving me this wonderful opportunity. I can say that I'm just more than happy to be joining with you today, and I will be more than happy even to present my recent research works on this topic today. And I also beg your pardon that I did not change the title in the short biography. The title of the talk today is Oxygen Electrocatalysis, the Holy Grail of Energy Storage and Conversion. And I beg your pardon for that one. And if you allow me, I can proceed. I think.
Please, sir. Please, you can go ahead.
Yeah, thank you. Yeah. I guess you can see my screen now. Yeah.
Please go. You can go ahead. Sir.
Yeah. Thank you. Very good afternoon to all. I'm sorry, very good morning. Here in Japan, it is afternoon. So, yeah, okay. Uh, as I was introduced, I have been working on material and molecular electrochemistry for the past 6 years, and I have learned something in this particular field of oxygen electrocatalysis. And today topic suggests, oxygen electrocatalysis is actually going to be the holy grail of energy conversion and storage in this particular time of highly developing nations, where we have so many number of highly developing nations, which growth totally depend on how much energy they get per capita and how efficiently they are replacing it. Since it has been said, we all know that we are depending mostly on carbonaceous fuels, and which are on the verge of total depletion. So it is time for us to go for alternative energy conversion and storage technology, which will free us from the future disaster that we are heading into by not turning our attention out of carbonaceous fuels. So that's what our thing, and we wanted to perform few research works which we believe that will be very useful in the future transition of carbon economy to a hydrogen economy. So having said that, I would like to begin my talk. So before going into oxygen electrocatalysis, I would like to first explain what is the concept of hydrogen economy first, and why it is needed, and what it will give as an impact to the future generation if we adopt this hydrogen economy concept. So since we all know that we are currently depending mostly on carbonaceous fuels like coal, gas, oil, as you can see from this World Energy Survey for the year 2017 to 2015, you can see the energy reserve, and the stock is going to decline very rapidly. And as you can see here, the oil is going to be depleted completely by the year 2050, and gas will be out of earth crust by 2060, and we will have coal hardly for another 60 years. So since we are totally depending on these three form of carbons for all our energy needs today, almost for all our energy needs today, so we are definitely heading into a big catastrophe in future by not diverting our attention to alternative energy and conversion technologies. So very few people now have started realizing that this is not the correct way to depend solely on the carbonaceous fuel. So people have started working on renewable energies. We know that renewable energies are far better than all other resources of energy like nuclear and carbon, because it does not affect our environment, and it is not going to be uh, uh, increasing the global average temperature and causing all other climatic issues. So we are going to depend totally on nature when we talk about renewable energy sources. But there is a issue. When we say about renewable energy sources, we are going to depend on the natural resources like solar, wind, tidal, and geothermal. These energies are not always consistent. They are not available throughout the year. They are intermittent, which means that we cannot rely on them for all our needs at all the time. For example, if we are depending on the solar energy, it is available in the daytime, and we need some other storing mechanism to use that energy during the night time. So it definitely says something that we cannot rely only on the renewable energy sources for our future needs. So we need an alternative energy storage as well as energy conversion mechanism, which will help us to store this intermittent energy when they are available in abundant in a particular season of an year. So we can store it in an electrochemical cell or a capacitor or some other fuels, which can be again used to generate electricity. So this was the total idea. So in this idea, people came to realize that hydrogen can be an efficient candidate in by which in the form of which energy can be stored. Energy, I mean the intermittent energies. I mean solar energy, wind energy, and geothermal energy, whatever the energy that we use to generate electricity, they can be stored in the form of hydrogen fuel, and which can be used for so many other applications. So that's what this whole diagram is talking about. And we know that uh, we have electrochemical capacitors and electrochemical batteries, rechargeable batteries, but uh, they are not so efficient. Efficient in the sense You can still store electrochemical energy in the in battery and supercapacitor, but the amount of energy that we are producing every day globally, the electrical energy, when you compare that amount to the amount of energy that we can store with the batteries, it is not even uh, just point. It is about just 0.1%. So clearly, batteries and capacitors cannot help us to store a large amount of energy. Consider about the polar region and the subarctic nation, which have uh, access to the solar light only for a 6 to 9 months of an year. They are under darkness almost for 3 months. So they need some sort of large energy storage mechanism, and people have come up with so many other ideas like flow batteries and mega grids using the combinations of so many batteries like lithium ion battery, which a kind of which was recently built by Tesla Corporation in Australia. People are doing so many other things, but still they are requiring more amount of source material for making the batteries and for more amount of human resources for maintaining those grids, and so many other things are there. Similarly, we have alternate option in which we can use this excess electricity which is generated from these intermittent energy sources to split water molecule into hydrogen just by applying the excess electricity that we generate from intermittent energy sources. In this case, what we are doing is actually we are splitting water, and it is generating oxygen and hydrogen. Which means that we are storing energy in the form of hydrogen, which can be used again in fuel cells to get power back, the electric power back, or it can be used for some other application like hydrogen vehicles and so for making synthetic fuels using carbon monoxide and carbon dioxide. And we can also upgrade the existing carbonaceous fuel source by hydrogenating them, and we can also produce other industrially important chemicals like ammonia and other hydrogen containing small molecules, and we can also use this hydrogen for metal refinery, and we can use hydrogen for so many other applications in fine chemical synthesis. So hydrogen clearly has a variety of promises which can be used in a variety of fields. So it is as of now appearing as a potential candidate for storing energy, the intermittent energy, excess intermittent energy as hydrogen fuel. And this is what we call the hydrogen economy. So just realize this thing. If this happens in near future and we are not at all depending on the coal and gas, oil, which are rapidly getting depleted by the increased, or I can say exponentially increased use of this energy sources in recent days. So if we succeed in this attempt, we will be totally transitioning into something called hydrogen economy, which will be our future. So this is the most important thing that we need to know before going into uh, uh, know about the oxygen electrocatalysis. So, and how does oxygen electrocatalysis uh, determines the success rate of this hydrogen economy. So let's move on to the next slide. Uh, Before going to that, we know oxygen is a very important gas in our atmosphere, which is the livelihood of all living organisms. We know almost all living organisms. These are some interesting facts about oxygen. As we know, this is the third most abundant element in the universe, and it reacts very rigorously when it is in nascent form, which means just as a single oxygen atom. And it is also highly reactive still when it is in molecular form. And it is always existing in diatomic molecule in the atmosphere, and we have 20.95% of oxygen in our atmosphere. If you see in the periodic table, almost every element in the periodic table exists as their oxide in the earth crust. There are only very few exceptions, which includes the net gases and noble metals. And half of their crust is made of oxygen, of course, since it is the third most abundant element in the universe. It is not a surprising one. And if you take biological living organism, whatever the protein you see, carbohydrate you analyze, and nucleic acid you segregate from the nucleus of various living beings, they all contain oxygen in major proportion. Beyond that, the hard shells, bones, teeth, and of every living organism, they all contain oxygen. So oxygen is something that we cannot live without it, and we cannot sustain without it. So this same oxygen is also going to determine our fate in the future from not getting destroyed by the catastrophe that we are heading into by depending only on the carbonaceous fossil fuels. So as you see, oxygen is very important. they are the actual backbone of this important three process that are very important in today's life: respiration, combustion, which in which oxygen is consumed, and we know photosynthesis, by which the atmospheric oxygen is continuously being replenished by the plants and whatever the living organism that have chlorophyll. So oxygen is that much important, and that's why it is going to, and the same oxygen is also going to determine our fate in the future as a mean for energy storage and energy conversion mechanism. So as I said, energy conversion and storage, we must first get a gist of what is the difference between energy conversion and storage. So I have listed out a few fuel forming and fuel consuming reactions, as you can see here, and these reactions can be considered as energy conversion and storage processes. Fuel forming reactions can also be considered as energy conversion process. As you can see here, I have listed out a few reactions: oxygen reduction reaction, hydrogen oxidation reaction, methanol oxidation, and oxidation of hydrogen, ammonia, boron, methane. All this oxidation reaction comes under fuel consuming reaction, and almost all these reactions are employed in direct fuel cells. If you employ hydrogen and oxygen, that will be hydrogen oxygen fuel cell, methanol oxidation fuel cell, such as that. But whatever the fuel that you employ in the fuel cell, that will become the fuel cell of its kind. So all this oxidation reaction, oxidation of small molecule, they come under fuel consuming energy conversion reaction. So if you consider the fuel forming energy consuming reaction, or which can also be regarded as energy storage mechanism, we have oxygen evolution reaction, which produce hydrogen and at the cathode, which is termed as hydrogen evolution reaction. And beyond this, you can also use electric energy that are generated from intermittent energy sources when they are available in excess amount, which can be used to reduce nitrogen to make hydrogen, ammonia, and if you co-reduce nitrogen and CO2 together, you can even produce urea electrochemically. And we have CO2 reduction, which is a very hot field of research now. So many people around the globe are actively working on this one. And hydrogen oxidation reaction, of course, reduces the overall cell voltage of hydrogen production by acting as a masking reaction for oxygen evolution in water electrolysis. And we also have ammonia oxidation reaction, which can also be used to generate hydrogen. So it is also a reaction which is forming fuel. And we have boron oxidation reaction. When I say boron, it is not boron. It is usually the adduct of ammonia and boron, which is also producing hydrogen when it is oxidized electrochemically. So all this fuel forming reaction and fuel consuming reaction, they can be regarded as energy conversion and energy storage reaction. So among all these reaction, these four reaction, the first four reaction, oxygen reduction reaction, hydrogen oxidation reaction, and oxygen evolution reaction, and hydrogen evolution reaction. These four reactions are going to constitute a major part of the hydrogen economy in the future. And we are about to see how oxygen electrocatalysis is very important in the succeeding in this attempt of transitioning from carbon-based economy to hydrogen economy. So, yeah. So we now know what is the concept of hydrogen economy and why we need to transition from the carbon-based economy to hydrogen-based economy, and how oxygen electrocatalysis is going to determine the success rate in the attempt of transitioning into hydrogen economy. So now I wish to show you a few ways of storing electrical energy. We know conventionally we can store electrical energy in batteries, and we also have capacitors, and we can store as fuels. So fuels in the sense any molecule, any small molecule that can be used later to produce the energy back can be regarded as fuels, and that fuel can be used in the future to generate power back either by an electrochemical reaction or by a combustion reaction. It could be anything. So all that you do here is you are storing electrical energy in terms of fuels just by performing a electrochemical conversion. So this is a new topic which is getting a greater attention in recent days. Yes. So in batteries, we all know the very famous lithium-ion battery, which uses lithium cobalt oxide anode or lithium iron phosphate anode. They are actually the state of the art in today's battery technology, and we all know that the recent Nobel laureates who got Nobel prizes in chemistry were awarded for the developments of this lithium-ion battery, and because these lithium-ion batteries are the ones which turned our whole technology thing to a newer level. Because before, if you see, before 2 decades, we don't have very compact electronic devices in our hands. It all happened only because of efficient storage mechanism, which is nothing but the lithium-ion batteries, which made everything possible. So even then, these lithium-ion batteries may be looking like a superhero at this stage, but they are not uh, up to the requirement level. Uh, I mean, up to the requirement level of storing a large amount of energy for our later needs. So, if you even if you make a megawatt or a gigawatt capacity having grids out of these lithium-ion batteries, you will be requiring a very high and sophisticated maintenance process, and you will also need to spend a lot of energy for that one. So, for miniaturized devices, these batteries are very good, but not for large scale energy storage. And the same is applicable for capacitors. So these two, we can say these two obviously are not going to play a major part in the future energy scenario. I mean, when compared to the hydrogen economy. Of course, this will be there in the future. I'm not telling that this will not be there. This will be there in the future, assisting the transitioning from carbon economy to hydrogen economy, but this will not play the major role in my view. So you should keep this in mind in my view. And we have the electrolysis of small molecules, and this is what uh, I'm going to stress a lot. So let's proceed. So as I have said here, these are the processes that depend on oxygen electrochemistry. As you can see, this is a simple um, the graphical animation of fuel cells and how a fuel cell works, and this is a simple graphical animation of water electrolysis and how water electrolysis works when we apply energy derived from sun or some other energy source. And this is the schematic of metal air batteries, which is advanced electrochemical cell, I can say, a battery which can store energy more efficiently, even better than lithium-ion batteries, as have the promise of high specific capacity and high energy density. So I will be talking about these three technologies and how oxygen electrochemistry is very important in determining the efficiency of these three technology and how it will be determining the fate of uh, the hydrogen economy transition. So this is what I'm going to talk about today, and let's start with the oxygen electrochemistry. So we all know that oxygen is a very important part in our all living organism, and it also constitutes a major part in Earth's crust. So there is no surprise that this particular element is important in energy storage and energy conversion. As you can see, I have listed out the reactions of oxygen, which is involving molecular oxygen, and those which are involving water molecule. So I have actually classified into two categories: oxygen electrochemical reactions that are involving actually oxygen molecule, and oxygen electrochemical reaction that are involving water molecule. As you can see, uh, there you can perform this reaction by controlling the number of electron transferred in each reaction, either the reduction or oxidation. You will end up with the different kinds of products, as you can see. So among these four different pathways of reducing oxygen or oxidizing water, we have the very first one, 4 electron path, which is very, very important. And this is the one, these two are the these two are the ones which are going to determine how efficient is the fuel cell going to be and how efficiently we are able to generate hydrogen from water. So these two are going to determine both generation of hydrogen and consumption of hydrogen afterwards in the fuel cell. So it is very important to know about this electrochemistry of electrochemical reactions of oxygen. So I have told that 4 electron oxygen electrochemistry is very important, and this is particular graph was taken from Professor M.T.M. Cooper's book chapter of fuel cell science. As you can see, um, 4 reactions are graphically illustrated here, in which this is the hydrogen oxidation reaction, and this is the oxygen reduction reaction, which are diffusion limited. Don't worry about the technical terms I say about the diffusion limitation and other things. You can ask me later if you wish to know further. And these two reactions are the ones which actually determines the cell voltage in fuel cell and also determines the efficiency of fuel cell. How efficiently you are generating power back from the fuel that you are getting from water electrolysis. Other than these two, we have hydrogen evolution reaction. Here, and oxygen evolution reaction here. This is the most important reaction if you consider water electrolysis, because this is the reaction which is going to provide us the desired hydrogen fuel. But if you want this reaction to happen with a very minimum over potential, you want this particular reaction to happen with a very low over potential, so that the overall cell voltage will be very minimum and you will be losing very small energy while generating hydrogen, in addition to the energy that is actually required for splitting water molecule. So in that sense, when I say the actual energy required is just 1.23 volt, because we know that hydrogen evolution should occur at 0 volt and oxygen evolution reaction should occur at 1.23 volt. So this means that by applying 1.23 volt, you must be able to split water into oxygen and hydrogen, generating hydrogen fuel. But in real cases, there are kinetic and thermodynamic complications, and we are also generating gaseous products out of liquid reagents, which means that we are increasing entropy. So altogether, indicating that we will not be able to split water just by applying the exact potential required, which is calculated by considering only the thermodynamic factors. So which means that we have to apply extra energy, which is known technically as over potential. As you can see, hydrogen evolution can start at 0 volt, but to have sufficient amount or rate of production of hydrogen, you need to apply some excess potential, which is called hydrogen over potential. And in the case of oxygen evolution, it is when you compare this oxygen evolution reaction with the hydrogen evolution reaction, it is kinetically very complex reaction. It involves more than one intermediate steps, among which each of them has its own activation energy, and when they combine together, they never occur at 1.23 volt at any given catalyst. So we always needed some amount of additional energy which has to be applied in the form of over potential. So when you actually generate hydrogen from water electrolysis, you lose some energy here and you also lose some energy here. Again, when you combine hydrogen generated by this reaction and oxygen generated by this reaction in a fuel cell, you are going to lose some energy here and you are going to lose some energy here. So overall, in this process, we are losing energy by both generating hydrogen from water, by getting back the energy from hydrogen and oxygen. So the overall process is highly energy consuming. So this is one of the crucial factors which is so far hindering further developments of this particular field of research. And people are cautiously working on that one, and they have come up with so many other alternative possibilities with which we can improve the efficiency of both fuel cells and water electrolysis, which include high temperature operation and so many others, which I'm not covering today. So I'll be just leaving it aside here. So we'll just concentrate on the reaction, electrochemical reactions that involve only oxygen. So here, the water oxidation, very important for water electrolysis, which determines the efficiency of water electrolysis. Here, oxygen reduction reaction, which is very important for fuel cell, which determines the efficiency of fuel cell. But when you see metal air batteries, both these reactions are important, because in metal air battery, we have to reduce oxygen during discharge, and we have to oxidize the hydroxide molecule which have been formed during discharge back to oxygen during charging. So these two reactions are very important in metal air batteries. So I'll be explaining it one by one. And before going into that, we should also understand the difference between electrolysis and catalytic electrolysis, because I said that electrolysis can be done by just by applying a potential. And this is an example video. You can actually, you can actually see that here a person is performing water electrolysis with a simple experiment. He took a cup of a plastic cup in which he inserted two nails from the bottom, and he's going to use that nails as electrodes, anodes and cathodes, and he is using a 9 volt alkaline battery here. As you can see, he just connects the nails onto the batteries and he pours it with water. Now you can see, once he touches the nails with the battery, you can see the evolution of gases, and those are nothing but hydrogen and oxygen. And this is, so that's what he has seen. And this is an example of electrolysis, where he just took some random material which can conduct electricity, and he also applied a very large potential of 9 volt, which is not an energy efficient way, and generated hydrogen. So this is just an example of electrolysis. But what is catalytic electrolysis and why is it so important? we must know this thing, because as I have just explained that this is going to be an energy consuming process. Even when you apply such low over potential, just think of it. When you apply such a large voltage and perform electrolysis, what will be the energy efficiency? We don't have to think of such thing. So we always must abide by the principle of catalytic electrolysis. So catalytic electrolysis is nothing but this is done. Electrolysis is done just by applying the exact potential or current which is actually required. So that we are avoiding excess energy loss, and we achieve this thing by optimizing catalyst and by interplaying with the catalyst work function, bonding, energy of interactions of intermediate, and thereby we are ensuring energy and cost efficiency. So this is the these are the difference between just electrolysis and catalytic electrolysis. So yeah. Let's now see fuel cells and oxygen electrochemistry. So I have explained the major process that depend on oxygen electrochemistry and how they are going to determine the future transition into hydrogen economy. Now we will see fuel cells and oxygen electrochemistry. And you have seen this animation in my earlier slides. You can see this is the process which depends on two electrochemical reaction. One is the oxidation of hydrogen to proton and electron, in which the electron is drawn out of the circuit or drawn out of the electrode and pass through a circuit where you use this electrons at the flow of electrons, which we know as current, to for our domestic needs. And this proton, which is produced in the solution near the catalyst, will be transferred to the another electrode, which is known as the cathode, and where oxygen is getting reduced by the externally directed electron and with the proton to produce water again. So in fuel cell technology, what we usually do is we take hydrogen and oxidize it at anode, and we take oxygen and reduce it at cathode, which produce water back. So by splitting this water again, we can get this fuel. But the overall process is going to be energy consuming. So people are working on that particular aspect, how to reduce this energy consuming hydrogen oxidation and oxygen reduction reaction, and hydrogen evolution and oxygen evolution reaction. When you compare the hydrogen oxidation and hydrogen evolution with oxygen evolution and oxygen reduction, this reaction, oxygen involving electrocatalytic reaction, I mean the OER, oxygen evolution reaction and oxygen reduction reaction. What you see here is oxygen reduction reaction are the most complex reaction kinetically when you see the kinetic aspects, and they are the ones which are consuming more amount of energy, and this electrocatalytic reaction should be improved in terms of kinetics, in terms of activity, and in terms of selectivity to ensure that the fuel cells and water electrolyzers are operating at its full capacity and losing minimum energy in producing hydrogen and in generating power when we use that hydrogen back in fuel cell. So this is what the fuel cell is all about, and that's how oxygen is going to determine its efficiency. In fuel cell, we need 4 electron path, which must be concerted one. It should not happen one by one electron, 2 electron, 3 electron, not like that. It should happen in a concerted fashion, and we should always decide for low over potential for a ORR catalyst, and ORR catalyst must avoid generating PROS. PROS is nothing but the potentially reactive oxygen species. Some people also term them as partially reduced oxygen species. So these partially reduced oxygen species or potentially reactive oxygen species can lead to so many other complications, including the destruction of electrode material, membrane, and so many other things. So we should be very careful about this one. And beyond that, proton conduction through this membrane and hydrogen oxidation, the efficiency of hydrogen oxidation, are also equally important in determining the fuel cells efficiency. But when you compare the importance of oxygen reduction reaction, they are equally, they are relatively okay, because they have facile kinetics, and we have many proton exchange membranes now, which are, I can say they are quite mature. The development in this particular field of proton exchange membrane is quite mature. So now we will say something about the electrochemistry and the possible mechanism of 4 electron ORR, because 4 electron ORR is the one which is highly desired for fuel cell. There are 3 possible mechanisms for reducing oxygen, in which oxygen can undergo dissociation after combining with an active site, as you can see here, and finally producing water molecule, by which we can get current by the electrons which are evolved out of the oxygen adsorbed on catalytic side. And we have peroxide dissociation mechanism in which it does not dissociate at adsorbed oxygen state. It moves on to the hydroperoxide intermediate formation with single electron reduction, which then undergoes various steps of intermediate reaction, producing water at the end, giving us energy. And we also have hydrogen peroxide dissociation, which is similar to this one, but instead of this step, we have hydrogen peroxide formation, which can further be reduced to water by producing energy. So these are the three possible mechanisms for 4-electron ORR, which are all identified to be happening in fuel cells, and of which the most facile one is the first oxygen dissociation mechanism. But finding a material for this particular mechanism following catalytic oxygen reduction is very rare, and people are working on that one. There are so many research going on this particular field. If you are still interested, you can read this paper, and there are so many other good reviews for knowing about the mechanism of 4-electron ORR. And so it is now important to know about the materials which can catalyze this 4-electron ORR reaction efficiently. And here I have given two graphs, which are basically the volcanoplots of metals and alloys. As you can see, volcanoplots can be obtained by various means. You can plot the activity against the standard electrode potential determined theoretically, or you can also plot limiting potential and the activity against the free energy change associated with a particular intermediate reaction, or the difference between two subsequent intermediate reactions between two different materials. As you can see, the highly active material will be the one which occupies the apex position or a top position of the volcano. So if you see, PT is obviously the best material for ORR when you consider only metal, and people have tried allying PT with so many other materials in order to improve its activity, and also with an objective to lower the amount of PT used in a total catalyst content. And people found that platinum yttrium, platinum nickel, platinum cobalt, and platinum scandium, those are all few materials which can perform better OER than just platinum, as you can see. So these are the trends in 4-electron ORR catalysts. Other than that, we also have metal oxides and perovskites and so many other catalysts which I have not listed. And there is one more crucial thing in determining the activity trend of ORR catalyst, which is the influence of EG electrons in the molecular level. I believe that most of you learned crystal field splitting theory, and you also know how does the octahedral complexes split their d electrons. The metal center split its d orbital into T2G and EG orbitals, and we have learned a lot about this particular property of coordination complexes and compounds formed by transition metals. And people have found that there is a very strong correlation between the occupancy of electrons in the EG orbital with the activity. And they found that either it is perovskite materials such as these ones, or spinel materials such as these ones, they always show higher activity when the EG electron population is close to 1, not exactly 1, as you can see here. And the same is true here also. So this is something people have found very interesting, and people, after finding out this thing, people have done so many modification and optimization and improvisation to improve the performance of ORR catalysts, and they are actually succeeding in it. And when you compare the developments made a decade earlier in this particular field, it is now far developed. So it is indicating that we are not very far away from successfully transitioning into the hydrogen economy. So this will help us to design and fabricate efficient fuel cell, which can help us to generate power back from the hydrogen generated from water electrolysis. So we have theoretical modeling which can predict the activity just by plotting the limiting potential with the free energy changes of the intermediate steps, and we also have this particular interesting correlation between EG electron occupancy with type of compound form. And now we have seen that oxygen reduction reaction, oxygen electrochemistry, the reduction was very important in fuel cell, and the oxygen evolution from water is also very important in ensuring energy efficiency of hydrogen generation, and that's what we are going to see from now on. Yeah, this is a simple graphic. As you can see, an intermittent energy is converted into electric energy using a photovoltaic cell, solar PV, and you are supplying the electron to reduce proton generated as a result of oxidation of two water molecules at the anode, and which are reduced to hydrogen molecule stored at different container. And you can also store, yeah, if you wish store oxygen separately, and you can use them for fuel cell application. So this is the fundamental working mechanism of water electrolysis. And I also told water electrolysis should be done in a catalytic fashion in order to ensure energy efficiency. So just like fuel cell and ORR, water oxidation, OER, should also be a 4 electron path and must be a concerted one. And we also need low over potential to ensure low cell voltage. And in the case of fuel cell, lower over potential of ORR ensure high cell voltage, which is very important in determining efficiency. But in the case of water electrolysis, lower over potential ensures lower cell voltage, which is important to ensure energy efficiency. Yeah. So we also have seen that the process could be detrimental to electrode materials in the case of ORR, and the same is true in the case of OER too, because process can also be generated via water oxidation. Remember, process something I said as potentially reactive oxygen species, the term which I like the most when I compare the another term, partially reduced oxygen species, because those can be generated only by the reduction of oxygen, but this can be potentially reactive oxygen species can be generated by both reduction of oxygen and also by the oxidation of water. So this is the most suitable term in my view. And we also have proton conduction efficiency through membrane and HER. Those are also important. So these are the important characteristic of ensuring energy efficiency in hydrogen generation via water electrolysis. And this is largely depending on the water oxidation reaction, which must be a 4 electron process. So we know that water oxidation also occurs at 1.229 volt versus RHC, and we must understand the mechanism by which it occurs. There are so many mechanisms. Even if you see the old, very old literatures, there are more than 5 different mechanisms for water oxidation, separately for alkaline medium and acidic medium. So I must have told this earlier. Water electrolysis cannot be done efficiently in neutral medium, waters which have neutral pH, because of the kinetic complexity. One more thing, we can also do, we can also not perform water electrolysis with pure water, because pure water is highly resistive, which has 8.2 megaohm per centimeter square as resistance. So we need supporting electrolyte. Even if you are supporting electrolyte in neutral medium, most of the catalysts which can evolve hydrogen and oxygen are performing very poorly with very low current density, increasing the energy loss. So making it as a poor process for hydrogen generation. But people are still interested in neutral water splitting, because those are the reaction which is going to be used in photocatalytic and photoelectrocatalytic water splitting for hydrogen direct solar fuel generation. So still neutral water splitting is important. But when you say electrocatalytic water splitting, you must stick either to alkaline condition or acidic condition. In acidic condition, the HER and PT surface is very facile, but we have very limited number of catalysts which can perform OER on the anode side. And if you choose the alkali, in the case of alkaline condition, we have a variety of catalysts for OER for the anode. But if you consider the HER reaction at the cathode is very poor in alkaline condition because of the absence of proton. So there are very few materials which can perform HER efficiently in alkaline medium. So both this method, alkaline water electrolysis and acidic water electrolysis, have their own advantages and disadvantages, and people are actively working on both of them. So the overall aim is to reduce the amount of energy lost during water electrolysis in the attempt of generating greener hydrogen. So this is the overall idea. And these two mechanisms are the ones which are most accepted widely by the people who work on this particular field. And we will specifically see the mechanisms of 4-electron OER and 3 materials. The first two will be ruthenium oxide and iridium oxide, which are known to be very highly active catalysts for OER in acidic condition, because they perform OER at very high oxidation state when we apply potential, so that ensuring oxidation of water very easily. So this is the mechanism of ruthenium oxide catalyzed water oxidation. As you can see, when we take ruthenium oxide hydroxide, ruthenium oxide, it immediately get oxidized to ruthenium 6 plus state, which loses a proton and electron to form ruthenium 7, which again loses another electron and proton, forming ruthenium 8. This ruthenium tetroxide is analogous to that of osmium tetroxide and highly poisonous, just as osmium tetroxide. But this is the one which is going to evolve oxygen by taking up a water molecule or coordinating with a water molecule, forming this adduct, which can again coordinate with another water molecule to produce oxygen, and again producing the same material. So this catalytic cycle will go on forever and ever. So as long as you apply the desired potential. But the problem is here there is an additional mechanism by which this material can get depleted, which is nothing but the volatile nature of ruthenium tetroxide. So this is a poisonous gas. So whenever you try to work on water electrolysis with this particular material, you should ensure that there is no escaping of ruthenium tetroxide from the cell. On the other hand, we have iridium hydroxide, which is usually in the trivalent state, trivalent positive state, which gets oxidized to tetravalent state, and which actually catalyzes the OER in a similar fashion. As you see here, it is in the hexavalent state, from which it can dissolve into the solution by coordinating with the water molecule and releasing 2 protons, or it can evolve oxygen going back to the tetravalent state. So this is a mechanism. But when you compare the toxicity, iridium is relatively better than ruthenium. So these 2 mechanisms were actually revealed by Coates et al. In the 1980s, even before when I was born. So this is very old material, and these 2 material have ruled for more than 3 decades in this field of water electrolysis as anode catalyst. But problem with these materials are they are very scarce in their crust, and they are highly expensive. 1 gram of this particular material, ruthenium oxide and iridium oxide, it costs more than 1 lakh in Indian rupee. So just for hydrogen generation, which you are going to perform with an anode electrode of area more than 10 tens of meter square, you will need a lot of material of this material, which makes that, which means that the cost efficiency is going to be a difficult one, because it will increase the cost of production of hydrogen, which will not be afforded by the common people. So we are in a need to replace these 2 materials. So that's why people turn their attention from acidic water electrolysis to alkaline water electrolysis, in which nickel and iron oxides are very effective in catalyzing OER. So I have told oxide path and electrochemical oxide path are actually the most accepted mechanisms for OER, but the recent comprehension is something like that, like this. People have come up finally with these 2 type of mechanism. One is adsorbate evolution mechanism, and another one is lattice oxygen participation mechanism. So in this mechanism, as you can see, the whole reaction involves the oxidation and reduction of catalytic material, and it also, the catalyst itself also possessing some oxygen when we apply them. So it is not sure whether the oxygen which is originally belonged to the catalyst was also involving in the evolution of oxygen, or only the oxygen which comes from the water molecule is evolved in the oxygen. People did not know this thing until very recently. So people propose a few material follow this reaction pathway where the oxygen evolved is completely from water, not from the catalyst lattice oxygen. And people propose from this mechanism for a few materials in which they state that the oxygen which is evolved at the end actually containing a few from the lattice of the catalyst material itself. So there is a difference of opinion on this among researchers, and it is still being debated. And until this work was published, I can say, at least for nickel iron oxide hydroxide, which is the best catalyst for OER in alkaline condition. This work was published by Roy et al. Very recently, and this is one of the interesting and more systematically studied work. As you can see here, they made NaFe alloy by deposition, and they exposed in the first procedure, they exposed to oxygen, which is having an isotope of 16, oxygen 16 isotope. So they made a core shell particle, and then they again reduced it using hydrogen, with the water via cycling in OER condition. They formed metal hydroxide. In this metal hydroxide, all the oxygens are 16, oxygen 16 isotope. Remember this one, oxygen 16 isotope. But when they took this particular material, catalytic material having only oxygen 16 isotope, and then OER with water molecule that contain only O18 isotope, they found that evolved oxygen is having only O18, which means that the oxygen within the lattice are not participating in the oxygen evolution reaction with this material. This was further confirmed in a different experiment by procedure B, where they have done a similar oxidation process to form O16 having metal oxide, which was cycled in this O18 containing water, and they formed a mixture of O16 and O18 having metal hydroxide catalyst, which was when employed to oxygen evolution reaction with normal water, which has O16 isotope, they did not found any O18 isotope. So, regardless of the method by which the material is made, either with O16 isotope or just with O16 isotope of water molecule in OER cycling, the oxygen atom within the catalyst do not participate in the oxygen evolution reaction. This was a very interesting result published by Roy et al. In Nature Catalysis, and people are now people have now changed their perception of this particular reaction with this material, and now a series of works are going actively in USA and as well as in Japan, and we are all working on this one. And now also we need to know the transition 4 electron OER catalyst, just as the one I have showed in 4 electron ORR catalyst. As you can see, the volcanoplasts suggest us that ruthenium oxide, cobalt oxide, nickel oxide, these catalysts could be highly active for ORR, OER. And when you say some perovskites, strontium cobalt oxide, lanthanum nickel oxide, those are the found to be a good material for catalyzing this oxygen evolution reaction anodically with very minimum energy loss. So we also have similar correlation for EG electrons. I believe you remember the data I showed for EG electron occupancy and its role in determining the 4 electron ORR earlier. You can make a similar correlation of EG electron occupancy in 4 electron OER too. But unfortunately, this data is available only for perovskite materials, and you can see the best active materials are the ones which have EG electron occupancy from 1 to 1.5. So in the case of ORR, we saw that the EG electron occupancy from 0.5 to 1 was one were the best ones, and in the case of OER, the catalysts which have EG electrons occupancy from 1 to 1.5 are the best ones. So with this in mind, one can even design or generate a catalyst which can perform both OER and ORR as a bifunctional catalyst, of course. And similar correlation can be made with other catalysts, as I said earlier, but have not been done so far. And we also know that other catalysts could follow their own mechanism. That could be either adsorbate evolution mechanism or just like this nickel iron oxide reaction, it could be just adsorbate evolution mechanism or lattice oxygen participation mechanism. We still don't know. So these are the trends in 4 electron OER, and this is how oxygen electrochemistry of that involve oxidation of water molecule with 4 electron transfer is influencing the energy efficiency of hydrogen generation from water. And we have done so many works on this particular reaction, oxygen evolution reaction, and we have also published so many review articles which you can see here. If you want to know more about this particular reaction and the progress of OER, you can read this article, and you can also access my ORC ID, and you can read more about that there. Now we will move on to metal air batteries and oxygen electrochemistry. As I said that fuel cells depend on the oxygen reduction reaction, and water electrolysis depend on oxygen evolution reaction. But metal air battery is the one which depends on the both. So we will see how. This particular schematics shows that we have a metal anode which dissolve into the solution during discharge by giving out electrons, which are actually directed through an external circuit to cathode, where oxygen from the air is being reduced to hydroxide to form metal hydroxide with the metal which is getting dissolved or oxidized as anode. So this is the discharging mechanism. So it can be done either in aqueous medium. If it is in aqueous medium, the formed material will be hydroxide. If it is in non-aqueous medium, the formed material is going to be oxide, where you will not have hydroxide of the metal dissolved. You will just have the metal oxide here. So metal oxides have poor diffusion, so it may hinder the efficiency of the cell. Otherwise, non-aqueous solutions have other advantages like high cell voltage and other things, but both are decided and both are being thoroughly studied currently. But the thing is that we should understand that oxygen evolution and oxygen reduction both are important in the case of metal air battery, because during discharge we reduce oxygen, during charging we oxidize the reduced oxygen back to oxygen. So this is the mechanism of metal air battery, and here I have listed a few um, representative candidate of metal air system from lithium air to tin air. As you can see, lithium air is the one which can have highest theoretical specific energy, including the air electrode, and tin air will be the one with the lowest one. And their cell voltage is also equal, almost parallel to that of currently state of the art lithium ion battery. So they also have high cell voltage and also very high in specific energy, which means that these metal air batteries could be the other version of currently best performing lithium ion batteries. So when you see about lithium ion batteries, the beautiful thing about is that there people do not use metal anode. Metal, when I say metal, it is the lithium, the most vigorously reactive metal, the periodic table. So they avoid this issue with the lithium ion battery, and that's why we all have very safer electronic devices in our hands now. But in the case of metal air batteries, we have no other option than using metal anode, which are so far the efficient candidates. But people are still working on that one, and I believe that something like lithium ion will also have some kind of diluted metal anode with the carbon composite. Something like that will be out in future soon, I guess. So now we will see. Uh, Now we have seen that this particular air cathode is performing both oxygen evolution reaction during charging and oxygen reduction reaction during discharging, and its bifunctional activity is very important in determining the efficiency and specific capacity, open circuit voltage of these metal air batteries. So what we can do about it? So now we know metal air battery depend on both these things. So this is the discharging reaction and this is the charging reaction, and we have 1.229 volt for both the reaction. So what happens if your metal air battery, if your bifunctional catalyst is not performing this 4 electron reaction, it is performing some other reaction. For example, instead of 4 electron reduction, if it performs 2 electron reduction forming hydrogen peroxide, the standard electrode potential for 2 electron reduction is 0.7 volt, which means that the cathodic potential will be 0.7. If we assume that the material is reducing oxygen exactly at the reversible potential, it will be 0.7 volt, and your lithium or zinc anode will be having some potential. When you calculate the cell voltage, it is going to be very, very low. So 4 electron path is very important during discharge. Similarly, 4 electron path is also important during charging, because if you increase the anode potential during charging, it is again going to cost you more energy as you increase, as your material is not performing water oxidation efficiently with lower work potential. So we need a very good bifunctional catalyst for having a very good metal air battery system. So having said that, how to design such an efficient ORR catalyst? So that's the next obvious question. So what we can do? We have just seen ORR volcanoplasts and OER volcanoplasts, which suggested that depending on the free energy change, what we see between two subsequent intermediates reaction, we can predict the highly active materials from the modeling, and we can come to know which material could perform better in ORR and OER. So we have this volcanoplat, which are available in literature. Why don't we try just compositing? You take the best ORR catalyst and take the best OER catalyst here. Why don't you perform compositing? And you can apply that material as a bifunctional cathode, air cathode in metal air battery and achieve high efficiency, I mean high specific capacity and high energy density. But the issues are ORR catalysts which are performing ORR, the reductive potential, usually perform good when their surface characteristic is retained. But when we have a composited catalyst which can have part of ORR catalyst and part of OER catalyst, when you perform OER, this material, these materials can be oxidized to its oxides and hydroxide, which may not be as active as these metals in ORR when you do perform uh, discharging again. So which means that these composites could be actually destroyed during the charging and discharging cycle because of its instability in counter reaction. So this is the main issue with this compositing. But what we can do about it? So we can try another strategy, which is nothing but making binary catalyst. Binary in the sense you can make truly stable solid solutions. Instead of just mixing two different catalysts physically, you can actually make a catalyst which can perform both OER and ORR and can be a single solid solution. So here we have EG electron correlation as I shown in the earlier slide, and we have EG electron correlation for ORR and OER, and we know that catalysts which have EG electron occupancy from 1 to 1.5 are the best, and ORR catalysts which have EG electron occupancy from 0.5 to 1 are the best. So if you are able to formulate a catalyst by the combination of these two and having an EG electron occupancy of around 1, you could end up with the best OER or bifunctional catalyst, and it can be very helpful in realizing very high specific capacity and high energy density in metal air batteries. So this is what we can do just by understanding how oxygen electrochemistry works. You don't need to know anything else. You all that you need is you must understand the oxygen electrocatalysis and how does it occur on material surfaces. So that's what very important. So that's how 4-electron oxygen electrochemistry is very important in determining the efficiency of fuel cells and also the water electrolyzers and also the metal electrobatteries. So these are going to be playing important roles in future transition of hydrogen transition into hydrogen economy. So far we have seen only about the 4-electron oxygen electrochemistry. So what else can oxygen electrocatalysis offer us? So this is the next obvious question. So we know this slide, and I have shown this one. We have so far been talking about this particular 4-electron path, and we also have other paths which produce hydroxyl radical and hydrogen peroxide, also hydroperoxide radical. Hydroperoxide radical is usually produced biochemically in biological organs. This is a very good anti-aging radical, and it prevents us from so many other unwanted metabolic process and from aging too fast. So we have hydroxyl radical, but the formation of this one, hydrogen peroxide radical, is very difficult in electrochemical pathway, and people have observed the formation of this particular hydroperoxide radical in water rarely, but this can be observed in non-aqueous solutions like ionic liquid and soda, and there it will be just super oxide anion, radical anion. So which have its own application in various other fields, and we also have this hydroxyl radical which can be obtained by the 3-electron reduction of oxygen or single electron oxidation of water, which is very important in industrial bleaching, wastewater treatment, and the oxidation of organic contaminants like textile dyes and leather tanneries, so many other things, because the oxidation potential of this particular species is 2.3 volt. It's huge, which means that it can almost oxidize anything, whichever having standard relax potential lower than this one. So this is very important reaction, generating hydroxyl radical in water. We people know, those who work on electrochemistry, about the electrofenton process, which has been used to treat wastewater for a very long time since its discovery. And we now have the 2-electron oxidation and reduction of oxygen and water, which can produce hydrogen peroxide. Hydrogen peroxide, as we all know, that a very important chemical which is used in various fields, and this particular 2-electron path of oxygen electrochemistry can offer us an efficient way to produce this particular material in a more greener way. I can say more environmentally friendly way. So let's just see why H2O2 is needed and where it is used, and why we need to synthesize this particular chemical from by electrochemical means. I mean the electrochemical synthesis. So when you see about H2O2, this is used in various fields, from wastewater treatment to electronic industries, and the most important one is medical disinfection. We all know that during this pandemic of COVID-19, we are all in the need of disinfecting agents, which is usually the major part of which is usually ethanol, but it also contains a significant amount of hydrogen peroxide. And hydrogen peroxide is in use as medical disinfection since its discovery. But the issue with this hydrogen peroxide is that the way by which it is being produced. As we know that hydrogen peroxide is the greenest oxidizing agent, because whenever it is used to oxidize or bleach something, it produces only water, and it produces only water and oxygen. We all know that. And so this is the most greenest oxidizing agent. But when you compare bleach, sodium hypochlorite, it produces chlorine gas, sometimes cause eye irritation, and it may be poisonous to few people. But hydrogen peroxide is not like that. It is the most greenest oxidizing agent. But when you consider the way by which it is produced, the anthraquinone process, which is a century-old process, is highly detrimental and hazardous process, where people uh, actually hydrogenate anthraquinone and again oxidize it to produce hydrogen peroxide molecule. But this method uses a carcinogenic anthraquinone, and it should be performed as a batch process, and it requires distillation, and it also requires phase transfer catalyst to transfer the hydrogen peroxide produced in the organic layer to aqueous layer. And moreover, the solution which is produced by phase transfer and distillation is always highly concentrated in the range of 70 to 80%. When you have such highly concentrated solution of a H2O2 in your hand, it is equivalent to that you are holding trinitrotoluene in your hand, because it is equally explosive. And some explosion have been witnessed in the past too. So people are trying to decentralize the production of hydrogen peroxide from the anthraquinone process. So people proposed direct synthesis, in which they used hydrogen, pressurized hydrogen and oxygen, and a noble metal catalyst in a closed vessel. But the problem with this method is still explosive, because we used a mixture of hydrogen oxygen, and it produces hydrogen peroxide in a very low rate, and it requires noble metals. So the problems are not completely actually alleviated here. So what can we do about it? As an electrochemist, we can offer two different pathways, safe pathways to produce hydrogen peroxide. One by partial oxidation of water, I mean 2 electron oxidation and 2 electron reduction. So this method requires no carcinogen, no H2O2 mixture. It works at ambient condition, no high pressure and high temperature, no phase transfer catalyst, no distillation, no concentrated solution. All that you need is, you must have a catalyst which can perform selectively 2 electron oxygen electrochemistry and a battery. That's all. At the spot where you want to use hydrogen peroxide, you can just collect this electrode material which can perform 2 electron oxygen electrochemistry with a source of power, and you have the hydrogen peroxide you decide to have. So this is going to revolutionize the whole field of hydrogen peroxide production, transfer, and its use on the site of demand. So that's what oxygen electrochemistry can offer us beyond hydrogen generation. So now we have to see something about the strategies followed in 2 electron water oxidation, because we can produce hydrogen peroxide. The strategies are just two. One is stick with the catalyst that are having poor OER activity and increase the potential beyond 1.76 volt. So these are the two strategies. If you do this thing, you can achieve the production of hydrogen peroxide just by oxidizing water. And these are the catalysts which have been reported to be highly active and highly selective for hydrogen peroxide production through water. And this is the famous example, and a very recent report by Shi, which was published in Nature Communication, where they prepared bismuth vanadate, and which performed a very good electrocatalyst for hydrogen production. When they applied artificial solar light, it also performed as a very good photo electrocatalyst for hydrogen peroxide production. As you can see, when they apply it as just an electrocatalyst, it produced hydrogen peroxide with the selectivity of 70%, but when they apply light, the selectivity improved beyond 70%. It almost touched 100%, around 2.25 volt. So these are all giving us hope that we are not far away from generating materials and designing materials which can perform selectivity to electron oxidation by suppressing 4 electron oxygen evolution reaction, and giving us a safe and greener path to produce the truly greenest hydrogen peroxide. So this is going to be the future of water electrolysis, and we also have carbon-based material which can also perform a similar hydrogen peroxide production via water oxidation. This is a recent work by Zia, which was published in Nature Catalysis, where they just took the carbon fiber paper, which is a very common substrate electrode used in electrocatalysis, and they coated this carbon fiber paper with a different percentage of PTFE, Teflon powder, and they found that this has increased the hydrophobicity and trapped oxygen inside the layer, which helped to increase the selectivity for hydrogen peroxide production. They achieved the selectivity as high as 65% at 2.4 volt with a simple carbon fiber paper. And now we are going to see the strategies followed in designing 2-electron ORR catalyst, because by ORR also you can get H2O2, because ORR we know it has to be 4-electron pair in the case of fuel cell and metal air batteries, but it is not so when you consider the production of hydrogen peroxide. Usually ORR proceeds via this mode of binding, which favors the 4-electron ORR when you have closely packed catalytic sites. These are all ORR catalytic sites, and these are oxygen molecules. As you can see, they bond via this method by donating 2 electrons at the same time and bonding with 2 adjacent atoms of ORR sites. But how can you achieve the reduction of oxygen directly to hydrogen peroxide is isolating the ORR site. Isolating in the sense you place the ORR active element in a matrix of ORR inert host material, so that you are disabling the bonding mode of 4-electron ORR. So if you don't have adjacent and are closely packed catalytic sites, this mode of bonding is obviously eliminated, and we have only this mode of bonding, which can be very helpful in generating hydrogen. So this is the strategy followed in 2-electron ORR catalyst design, and people have done so many works, and there are just like ORR volcano, we have volcano floods for 2-electron oxygen reduction reaction, and people have also, these are all due to electronic effects, and people have also achieved selectivity just by following the strategy of isolation and inert host material. Here you can see various metal allied with the Hg, in which Hg is the ORR inert host material, and copper, platinum, Ag, those are the ORR catalytic set, and they predict that it can be achieved. The production of hydrogen peroxide via oxygen reduction can be achieved by diluting the catalytic site in ORR inert host material. And very recently, Young compared the free energy of hydroperoxide intermediate formation with oxide intermediate formation, and they found that the MNC catalyst of these 4 material are very highly active for selective 2-electron reduction, which can produce hydrogen peroxide efficiently. And these are some prototype electrochemical reactors which were recently proposed by Perry et al. In their recent review. And we have gas diffusion electrode, flow cells, helium proton exchange membrane fuel cells, and triple bed reactor, the aim of which are enabling the efficient and continuous production of hydrogen peroxide by a environmentally friendly and safer electrochemical synthesis method. So these are the developments that are occurring in this particular field, and it will go beyond that one. And we expect that this will be the hot topic in near future when you consider oxygen reduction and water oxidation. So let me summarize and conclude here. So I have been talking about oxygen electrochemistry a lot from the beginning. So I think you might have now understood that oxygen electrocatalysis is undoubtedly the holy grail of successfully transitioning into hydrogen economy, and oxygen evolving energy conversion reactions holds a lot of promises, ensuring carbon-free economy. And technically, so we can conclude like storing electrical energy in metal air cells depend largely on the oxygen electrode. That is true, and various fuel-consuming reactions are governed by oxygen electrocatalysis. And just by manipulating the number of electron transfer involved, you can actually revolutionize various other fields that can be industrial bleaching with hydroxyl radical, or hydrogen peroxide production, or energy conversion, or just energy storage in metal air battery. You can do so many things just by controlling the number of electron transferred in the electrochemical reactions that involve oxygen. So in future, theoretical modeling and in situ or operando analytical techniques are going to be very important to predict further trends in catalytic design and further growth and further development that could occur in this particular field of research. And yeah, as I said, this is definitely the holy grail of future energy conversion and storage. And if you have personal queries and discussion, if you are willing to have a discussion with me, you can write to me. You are always welcome, and I request you. And I recently started receiving mails very randomly without any formal information about the sender who sent me email. So I request you, please send whenever you send something to my email ID. Please introduce yourself clearly so that I would get an idea what you are actually looking for. Yeah. If you have queries and discussion, you can always write to me. You are most welcome. And it's time to acknowledge my funding supports. I have been receiving funding from the JSPS, Japan Society for the Promotion of Science, through JSPS postdoctoral fellowship since January 2019. I was also supported by CSIR India for my doctoral research work from April 2014 to October 2014. And these are my current group's senior researchers. And this is my current supervisor, Professor Noda, who are very supportive and have been encouraging me in all my works. And this is my mentor, PhD mentor, Dr. Subrata Kundu, without whom I could have not be here, or I could have not learned so many things without him. He was there always for me, and I should not forget my group members who supported me in all my needs, in all my situations. And I must not forget thanking my advanced electrochemistry coursework tutors, Professor Vijay Mohanan Pillai, who is in ISET Tirupati now, and Dr. V. Ganesh, Dr. J. Madhyarasu, Dr. Sheila Bergmans, whoever taught me electrochemistry that I use it today for my research works. And I also thank the host organization today, CIT, and Professor Dinagaran, and my good friend Dr. S. Puvaragan, and also Miss Harini, and also the chairman of CIT. And I hope I would get a lot of other opportunities to present my future works in their platform, and I would like to continue the collaboration with them. And yeah, thank you very much for your patience. And if you have questions now, you can shoot at me.
Yes, sir. Sir, thank you so much.
Thank you,
Very happy. Yes, sir. Yeah. Nicely, I think the presentation was very nice. I think you have put a lot of information. I think it might have taken a long time to prepare the presentation, and I hope there might be very good knowledge transfer to the researchers. I mean, a lot of researchers are attending this program, and I hope around 50 researchers are raising their hands to.
Yeah, I will answer them all. I will answer them. I have.
Let me allow some, sir. A few. I am.
Yeah. Okay. Yeah.
Dr. Balakrishnan, Dr. Kandiji, Dr. Keetha, Dr. Balamurugan, Dr. Pandiswaran, Dr. Muthuraman. You have been allowed to come and clarify your doubts. So please, you can come and ask your doubts. And after coming, please mute your mic. I will ask you one by one to clarify your doubt. Please.
Yes.
Yeah, Dr. Balakrishnan, you are on live, so you can ask your doubt with Dr. Anantharaj. So some disturbances in your sir, until he comes, we will
we can ask some of the questions. Yeah. Okay.
Mr. Jivananda had asked one question.
Yeah. Okay.
Once lithium gets over, what is the future for electronic devices?
Yeah, that is something that I don't think lithium will get over, because people are now actively working on the recovery of value-added materials from spent lithium-ion batteries. I know a few who actively working on that field, and people are recycling the lithium which are available from spent lithium-ion batteries. And I also read somewhere that among the e-products, electronic waste products produced every year in India, lithium is actually constituting more than 26%. So instead of just getting lithium from its ore, it is time to focus on sustainability by recovering the materials, lithium and other value-added materials from used lithium-ion batteries, which is going to ensure us further prolonging of lithium-based technology, electrochemical storage technology.
Yeah, great, sir. Great.
Yeah.
And no question. Mr. Balakrishnan, Dr. Balakrishnan, you can ask your question.
If he isn't available, you can give it to others, sir.
Yes, sir. Yes, sir. I have given. I allowed so many people.
Okay.
Sir, another question from Tirukumaran. Sir,
Okay.
can you use the new type of hydroelectric cell in hydrogen production and storage?
Hydroelectric cell. I have never heard of the term.
Okay.
Yeah, I'm sorry. I have never heard of the term. Hydroelectric cell. Yeah, I can. Okay. Yeah, I'm seeing from the comment too.
Yeah, sir. Yeah. Dr. R. Kandiji, you have joined the room, so you can ask your doubts.
Yeah. Yes, Dr. Gandhi, you can ask me.
Sir, Mr. Yeah, I think Gandhi, Dr. Gandhi.
Yes, sir.
You can ask your doubt to.
Yes, Dr. Gandhi, I'm here. Yeah, you can ask me.
Sir, until then, we will take one question. Youth Glory ask one question. So, why alkaline water electrolysis is better than acid water electrolysis?
Yeah, actually, there are two things. Alkaline medium is less corrosive than acidic medium, so that we are ensuring long lifetime of electrode materials. Second thing, in alkaline condition, we have a lot of non-precious and cheaper electrocatalysts for oxygen evolution reaction, which we don't have for acidic water electrolysis, which means that the cost efficiency of hydrogen production can be ensured in alkaline water splitting. So that's why alkaline water splitting is very important. And on the other hand, we have a problem in hydrogen evolution reaction in alkaline medium, which can be overcome with the new catalysts which have been reported recently. So in my view, hydrogen hydrogen generation from alkaline water is energy efficient and cost efficient when we compare the same with acidic electrocatalysis, acidic water electrolysis.
Yeah, Dr. Gandhi, if you are online, you can ask your question. Sir, another question.
Yeah, yes.
Mr. Naresh asked one question. Sir, you said iron and nickel are much effective in alkaline medium for electrocatalysis.
Yes.
But FEA-based catalysts are not good for OER, right? Is it so?
Yes. This is a very interesting question, and I have been working on that one. We found a very very interesting result too, and people have been working on this particular material. I mean, the nickel iron oxyhydroxide, and they found very interesting results that in oxygen evolution reaction, Fe acts as the actual OER catalyst, and nickel acts as the host material which provide the required conductivity. But when we have only iron, it forms the electronically insulating iron oxide hydroxide, which also makes it inefficient OER catalyst. So iron is the actual OER catalyst when it is present only in the suitable material like nickel oxide hydroxide or cobalt oxide hydroxide. When it is present alone, it is actually insulating and having a high resistance and behave very poorly in OER. So this is the one thing that has been discovered very recently, and people are working on that one. There are many in situ spectroelectrochemical and photoelectrochemical studies which shows the importance of having a suitable host material like nickel and cobalt with iron in order to achieve high activity. But when only iron is present, it is not active because it is forming insulating iron oxide hydroxide, which is not good for OER catalyst. There is a very recent report on Fe3S7, I think. Fe3S7, a type of an allotrope of iron sulfide. When it was applied to oxygen evolution reaction in alkali, they observed similar oxygen evolution enhancement which could be observed with nickel iron oxide hydroxide. And they examined that system and they found that the Fe3S7 system is actually acting just like nickel oxide hydroxide by providing the necessary conductivity, required conductivity for iron oxide hydroxide sites. So it is enhancing the oxygen evolution reaction. So iron is actually the better catalyst only when it is present with the suitable host material which can produce, or which can provide the necessary conductivity. So that is why nickel iron catalysts are very good and not only iron. Have I made it clear?
Yeah, it's clear. That is clear.
Sir,
and Dr. Kanti, you have been trying. So if your line is clear, you can ask. Okay, sir. Okay. So I am looking for any other question.
Yeah.
Sir, Mr. Karthik had asked one question.
Yeah.
How will be the power and the energy density consumption for using this system?
I have discussed about 3 systems. I don't know which system he specifically asked.
Okay.
Okay. In the case of metal air batteries, power and energy density totally depend on the performance of both anode and cathode material. In the case of oxygen, when we consider about the oxygen evolution reaction and oxygen reduction reaction, both are important, and our bifunctional catalyst should have very low over potential for both reactions in order to ensure high open circuit voltage during discharge and very low charging voltage during charging, so that we can ensure both power and energy density and also energy efficiency.
Okay, sir. Okay, sir. Thank you. And I have allowed so many people, but because of their connectivity, they have come inside, I believe.
Yes, I understand, sir. No problem. No issues, sir.
Yes, sir. Sir, thank you so much. Thank you
very much, sir. I must thank you and Dr. Purayan and CIT organization for giving me this opportunity, and I hope I would find some other occasion to join with you again.
We would like to hear you a lot from some other occasions, and we would like to lead some collaborative work if possible.
Yes,
sure. Since your friend Pura is already here,
we have already talked about
possible basic research here.
Yes.
So we'd like to hear from you regarding that too, sir. Thank you so much.
Thank you so much. Thank you very much, sir.
We will meet in some other occasion.
Thank you, sir.
Thank you so much. Thank you, participant. So your certificate will reach you within 2 nights. So thank you. We will see you in summer meeting. Tomorrow's meeting.